Good afternoon, everybody. I am Federica Buccino, Junior Research Assistant at the Department of Mechanical Engineering in Politecnico di Milano. And with this short trip inside human bones, I would like to introduce you to the pitch related to silk fibroin-based lacunar-inspired biomaterials for mini-invasive bone repair. Broken bones, broken lives. We are currently living in an aging society threatened by the burden of fragility fracture that effectively result in an enormous psychosocial and economic impact for the disease management. In this context, early diagnosis and targeted prevention are the keys. However, there is an intrinsic complexity linked to the multi-scale structure of bone architecture that arranges itself across different levels, starting from the macro scale, where we have the whole bone level, reaching the mesoscale, at which we distinguish both cortical and trabecular structure that are more porous, and the microscale, in which there is a dense network of osteocytes embedded inside ellipsoidal cavities named lacuna. Due to pathologies, an altered bone remodeling may occur. Specifically, this means that bone resorption is much higher than the physiological homeostatic bone formation. I have just presented you the orchestra of bone remodeling, which main actors are osteocytes, osteoblasts, and osteoclasts. State-of-the-art techniques for repairing an impaired bone remodeling, and specifically the presence of large bone fracture, is characterized by Ilizarov osteodestruction, bone autograft, and bone allograft. However, at present, none of them is able to restore the full function of bone. That implies both structural and architectural main constituents. The latest techniques specifically focus on the implementation of synthetic bone substitutes that are the sort of sponges that you see on the bottom right part of the slides, in which a structure called scaffold is cellularized by means of mesenchymal stem cells. However, when designing and realizing scaffolds, there are still a lot of aspects that needs to be deepened and considered. Therefore, in this framework, we mainly identified three huge open research questions. First of all, which is the effects of biological parameters on the design of a suitable cellularization approach when setting scaffolds? How to evaluate then the construct efficacy? And later on, which is the relationship, which are the crosstalks existent between the poor morphodensitometric feature of the scaffold itself and bone regeneration within the construct? To tackle these open questions, we use an approach that is based on mechanical testing, synchronous imaging, and advanced artificial intelligence-based model for the accurate detection of the new formed bone inside the construct. The scaffold realization technique is particularly challenging and focuses on the use of a novel biodegradable material that is the silk. Indeed, silk has optimal properties when inserted in the human body, and it is also biodegradable. The porosity inside the scaffold itself is generated by using a salt leaching method, in which we have a control on pore size, but we do not have control on the precise distribution of the porosity itself. In our research project, we decide to test our construct inside a synchrotron, which allows us to capture the three-dimensional architecture of the scaffold itself and the new formed bone at an unprecedented resolution. Tests are performed by means of an ex novo designed microcompression device, which is both human eye and X-ray transparent. It is particularly light, and it is compatible with the rotatory stage of electrosynchrotron in Trieste. Testing phase is the so-called image-guided failure assessment phase of the project, and it is conducted, as I've anticipated you, by using synchrotron facility. The chosen voxel size of 1.6 microns allows us to capture not only the porosity of the scaffold itself, but also new form bone inside the construct at a very, very high resolution. Specifically, using this high resolution allows us to capture the formation of mineralization site and specifically of lacunae. Several assays have been exploited to determine the cell seeding efficacy inside our construct. As an example, on the left, the AR assay allows us to determine in red the collagen filaments and in dark red the calcium that corresponds to the mineralized bone. On the right of the slide, you see again the scaffold depicted in gray and the new formed bone in red corresponding to type 1 collagen. It is worth pointing out that the main limitation of this assay is linked to their bidimensionality, that is overcome by means of a synchrotron technique. Indeed, as you can see from this slide, the unprecedented power of synchrotron image allows us to obtain a three-dimensional full reconstruction of the scaffold in green and the mineralized bone in yellow. Specifically on the left, you see FBS constructs that are that exploit the fetal bovine serum on the as a culture medium. On the contrary, on the right of our slide, you can see the HPL construct that exploits the presence of human plate lysate when culturing the cells. Much higher mineralization is effectively visible in the HPL construct. It is worth pointing out that what you can perceive just from a qualitative point of view from the previous three-dimensional reconstruction that are, however, characterized by an enormous computational effort, it can be immediately calculated synchrotron slice by synchrotron slice precisely at each one of the output synchrotron images. Therefore, once again, we are able to detect the correlation between the bone and the scaffold characteristics. This correlation cannot be done just slice by slice, but inside each slice, allowing us to define and to quantify the eventual crosstalks existing between poor morphological features and their three-dimensional distribution and the formation of mineralized bone. This could be done aided by artificial intelligence strategies, specifically in the form of convolutional neural networks. And now that we reach the end of our presentation, we can identify which are the main strengths, weaknesses, opportunities, and threats of this research project. For sure, we have been able with this methodological approach to determine which are the correlation existent between the poor morphodensitometric characteristics and the bone formation. On the contrary, the high computational costs in image post-processing should be considered. Artificial intelligence tools in the form of CNN, convolutional neural networks, have allowed us to overcome this issue. Synchrotron is and results specifically a powerful tool for construct validation. However, the next step of this research will focus on correlating our findings to the clinical practice. That means to translate our results to construct that should be later on implanted in the patient. And now I would deeply like to thank you for your attention and to acknowledge at the end this multidisciplinary group that allows us to perform all this analysis. Thank you.